5, the Atwood machine. An Atwood machine, it's actually a theoretical, mythical machine. It's a pulley system, as seen below, where you have mass 2 and mass 1 hanging from a rope around a pulley. But the reason, Sam, it's technically a mythical and imaginary, our pulley has no mass, because that would change the question and make the math yucky. Oh, and our ropes have no mass, because that would change the question and make the math yucky. And do you know how much friction our pulley has? None. But it's a good theoretical wrap our brain around some physics concepts, and it does have some nice applications in the quote-unquote real world. So we use it all the time in elevators. In an elevator car, actually what we have somewhere is a counterweight that's about the same mass as an empty elevator car. So in this example, mass 2 would be the counterweight. And what that does is it means all that, if this is an engine, if the pulley is an electric motor, all it has to lift is the difference in masses. All the motor in an elevator car is lifting is generally the mass of the people, not the mass of the car itself. So you have a counterweight. Nice little system. So here's our first question. Suppose equal masses are placed on both sides of the Atwood machine, and one mass is lifted higher. So this is not an Atwood machine, but it's a good simile, except this has a huge amount of friction in my little pulley thing right here. So we do have two equal masses. So suppose I lift one higher as follows. Wrong way around. One higher as follows. And there's no friction here. And I let go. What's going to happen? Will the system remain at rest? Will the higher mass fall down? Will the higher mass go higher? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. Who says in Dueck the system's going to remain at rest? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just going to write lots. Who says the higher mass has to fall down because it wants to get to equilibrium? No one. Who says the higher mass goes higher? So I guess I'll say, yeah, A is right. Convince me. You started to raise your hand. Yes, sir.
Well, if the friction is zero and the ropes weigh nothing, then there's absolutely no forces acting on it, gravity on both sides.
I would totally accept that. Totally give you full, if I gave this to you as a using principles of physics right to explain question. Too much English. This is a job for a free body diagram. Well, you know what? This is a chance for me to label the forces on this diagram. So I'm going to call this mass 1, mass 2. What are the forces acting on mass 1? Get the obvious one. Is it in free fall? No. So there must be a force acting up. What? Tension. On mass 2, we have M2G. Tension. Who's winning? You know what? I'm not sure, but let's suppose that you were going to choose B. You thought the higher, which is the most common mistake in physics 11 that kids make. A lot of kids in physics 11 choose B. They want the higher mass to fall. Well, who would be winning if B was correct? That's not a force, that's a mass. Which force would be winning? Thank you, William. Say that again, please. So you'd say, I'm going to let this direction be winner. So you'd have M1G, but then you run into tension, which is a loser. Oh, but then you run into tension again, and although it's pointing up, when it gets over to the left-hand side, it will be pointing down. You run into tension, that tension is a winner. Oh, and although this M2G looks like it's pointing down, if you follow it across on this side, it would be pointing up. So it's a loser. Yes? So you end up with this. M1G minus M2G equals M1 plus M2 times A. Yes? Ah, but what did we say about both masses? How do they compare to each other? They're equal? So let's also make a comma. M1 equals M2. So this is really M1G take away M1G equals M1 plus M1 times A, since M1 and M2 are the same. What's the left-hand side work out to?
0.
Oh, because it's something take away itself. I have this. 0 equals, well, I'll leave it like this. M1 plus M2, M2, Mr. Dueck. M1 plus M1 times A. Look at the right-hand side. Can those masses possibly work out to 0 if I add them together? No. How can this equation be true if I have something times something results in 0? What must be 0 on the right-hand side? It's got to be the acceleration. Therefore, A has to be 0. In fact, you know what? The system could remain at rest, or if they were already moving, the system could keep going at a what? Constant speed. That would also be acceptable. What you can't have is an acceleration. William, you said it in English. There's a lovely algebraic proof. I could probably do it a couple lines shorter if I really, really thought about it, especially if I said M1 equals M2 at the beginning. I suspect I could get there on this line by just letting M be M be M be M be M. But there's a good algebraic, no English required explanation. Gotta be. What if they're not? Example 2. So in the diagram below, assume M2 equals 5.8, M1 equals 2.3. Solve for the acceleration, find the tension in the cord. All right. Suggestions? How have we started out almost every single forces question so far for the past few days? Free body, although since they gave me a diagram, I'm not going to rewrite a separate free body diagram, Kelly. I'm going to be a bit lazy. I'm going to label the forces on my actual diagram. What are the forces acting on mass 1? Get the obvious one. M1G. Tension pointing up because mass 1 is not in free fall. That's it. Not touching the ground, so no normal force. What are the forces acting on mass 2? Get the obvious one. M2G. Tension pointing up. Who's winning? Why? M2, you're correct. By the way, M2G. Why?
Because of the higher mass.
That's heavier. That's the one that's going to fall down. Okay. So that means I'm going to define anything that ends up pointing down when it gets to the right-hand side is going to be winner plus. Anything that ends up pointing up when it gets over to the right-hand side is going to be loser minus. Winner plus. Loser minus. Ah, what about this tension? Now, initially, it looks like it's a winner plus because it's pointing up, but follow it, follow it, follow it, follow it, follow it, and when it gets to this side, which way will it be pointing? Down, winner plus, instead of loser minus. And here I have, initially, it looks like it's pointing down, but Peter, can you see when I follow it, follow it, follow it, M1G, when it gets to the other side, is actually going to end up pointing which way? Loser. I mean the force, not you. Oh, and wait a minute. You didn't put your name on something. Maybe you... Never mind. We've listed all the forces. And we're looking at more than one mass. So it's going to be M1 plus M2 times A. Why am I so relaxed? Oh, I'm losing tension. I love it when I lose tension. She doesn't know that joke yet. Sorry, had to work it in. And you know what? I think we're good enough. Let's get the A by itself right now as well. How would I get the A by itself? Divide by the bracket? Sure. So if I hear you correctly, Curtis, Let's also call that part A. Find A. A equals mass 2g minus mass 1g divided by mass 1 plus mass 2. This actually also, William, goes back to your explanation. I could have written the acceleration on the previous question like this, and if mass 1 and mass 2 are the same, you can see clearly, yeah, I have to have 0. I get an acceleration of 0. Here, though, we got numbers is. Mass 2, 5.8, 9.8 minus mass 1, 2.3, 9.8 divided by 5.8 plus 2.3. Brackets around the top, brackets around the bottom. Get your calculators out. Crunch the numbers. What do you get? She spoke to me already. I think I gave you everything on your... I gave her the lesson 2 as well, yeah? Okay. What do you get?
4.2 meters per second squared.
Sorry?
4.2.
By the way, I know the answer is going to be less than 9.8. Pretty sure. It can't be in free fall. So there is a built-in, if you get an answer bigger than 9.8, you probably goofed. It's not free fall. Something's holding it back, right? Let me double check here. 5.8 times 9.8 minus 2.3 times 9.8, close bracket, divided by bracket. 5.8 plus 2.3, close bracket. 4.2345, that's right? So I'll go 4.23. Units.
Meters per second squared.
Direction. Trick question. You'll notice I didn't bother putting vector signs on my acceleration. The reason is, depends which mass you're looking at, Elijah. One of them's going up, one of them's going down. I said solve for the acceleration. I guess technically I should have said solve for the magnitude of the acceleration, but let's clue in. Anytime there's more than one mass, that's all you can find is the magnitude. I need to tell you which mass to look at to find a direction. Is that okay, Josh? What did part B want me to find?
Tension.
Go look at one mass. Doesn't matter which one. Petra, do you want to look at mass 1 or mass 2? By the way, before I say it doesn't matter which one, however, you'll usually find one of the masses is easier to find the tension with. What should I look at, mass 1 or mass 2, and how come? You got a 50-50 chance of guessing right. Nathan, which mass do you want me to look at? Mass 1 or mass 2?
Mass 1.
Convince me, why?
So,
What's winning? Is gravity winning?
No.
Mass 1's lighter, right? By the way, I agree with Nate. I would look at mass 1, but you know why? Because tension's winning, which means it's going to be easier to get by itself. That's me being really lazy. If you picked mass 2, Sam, fine. Because really, it's not going to take any extra work to get the T by itself, except in your head. And I'm so lazy right now that I'm even saying, you know what? I don't want to have to do extra work in my head, which is sad, but that's how I roll. Because it would be this. Nate, if I write for mass 1, who's winning? Who's losing? And I'm only looking at one mass now, so it's going to be M1A. Can you see, to get the tension by itself, I just plus it over. By the way, if you did mass 2, it would be mass 2G minus tension equals M2A. It's no extra writing. You're going to move that there, you're going to move that there, which I think all of you would do in your head anyhow. But Callum, I'm actually saying I'm lazy enough to avoid using extra brain power, which again is just sad. You get the same answer no matter what. Neve, how would I get the tension by itself? Plus it over. So if I hear you correctly, tension is going to be M1A plus M1G, which is going to be, what was mass 1? 2.3 times 4.23 plus 2.3 times 9.8. I gotta be honest, I'm gonna cheat since I have the answer button. I have the acceleration still stored. I'm gonna use my answer button. I'm gonna go 2.3 times answer plus 2.3 times 9.8. Why not negative 9.8? We took care of all the we're not going to use a negative 9.8 in a forces equation. We've taken care of that with our tug of war approach. Do you get 32.3? Yeah? No? Yes? And you'd get the same thing if you used the other mass. Before we turn the page, another question, unless I did it. Did I add it finally? Because I've been wanting to add it for quite a while. Maybe I finally added one. I didn't. God, how do I keep forgetting to do that? Maybe I added it to Physics 11. A nice twist. I like this question, instead of me giving you both masses, find the acceleration, find the tension, could you, if you knew the tension, find the acceleration if you knew one mass? And then could you find the other mass? There's some like that in your great big physics review package. And I think on one of my versions of a test, I give you an Atwood machine, but as a twist, I think either I give you the acceleration and I say find both masses, or I give you the tension for one mass. I say find the acceleration for that one mass. And now that you know the tension, the acceleration, go see if you can figure out what the other mass has to be. And it's going to be writing individual equations and solving. It's a nice little twist. Example 3. It says, consider the following system. Which of the following is the best force diagram for mass M2? Oh yeah, turn the page. All right. Well, since they're asking about force diagrams, why don't I try drawing a free body diagram? So here's a free body diagram for mass 2. What are the forces acting on it? Get the obvious one. Is it sinking into the ground like quicksand? Is it lifting into the air like Superman? Does that help at all? No, every single one of those looks like it has that. Every single option. What else? Force applied, I disagree with. And the reason I disagree with that is the force applied isn't touching mass 2, it's touching mass 1. I got to be fussy. I don't think force applied is what's making mass 2 accelerate. In fact, I know it's not. Friction? I have Elijah nodding. I have Cliff shaking his head. Friction, yes or no? Cliff, why did you say no friction? Elijah, why can we say no friction? Huh? So I don't think there's any force acting that way. I think I would say nuh-uh. Okay? And the most common mistake is kids say, hey, Mr. Dueck, B is right, B is wrong. Okay? The answer here is A. Now, what are the forces acting on mass 2? I agree, gravity down. I agree, normal force. I'm telling you, the applied force doesn't touch it. Doesn't touch it. What are the forces acting on mass 1? Get the obvious one. Gravity, normal force. There is an applied force pushing that way. What else? There's one more force acting on mass 1. William, say what? Are there two surfaces in contact? We said a normal force doesn't always have to be pointing up from the floor. A wall, remember the book Against the Glass with the meter stick? We said a wall, a vertical surface, can exert a perpendicular normal force as well. Now, because mass 2 is exerting a normal force on mass 1, What can you say about forces? What do they come in? This is actually the normal force of mass 1 on mass 2. I got to be really fussy. It is not the applied force. How do I know? Because the applied force isn't touching mass 2, is it? Okay. As mass 1 starts to move, it runs into mass 2. Mass 2 applies a normal force onto mass 1. And this is a little weird because a lot of people, Alex, well, normal force, oh, he's pointing up. No, your surface can be vertical, in which case, if you don't want to call it a normal force, call it a contact force. Call it, in fact, that might be something better. I may do that next time. Call it a contact force. Two objects come in contact with each other. They both push against each other. Same magnitude, opposite direction. Okay, so explain your answer using relevant physics principles. I think we just did. I'm not going to write out a big long explanation. I think here I would take a good free body diagram. Oh, example 4. I didn't call it a normal force. What kind of a force did I call it in example 4? A contact force. So it wants us to find the contact force between the two blocks. Okay. This is a little bit different. No rope attaching them. But you know what? Although this looks tougher, in some ways this is easier. Say what? Ashley, are these two masses touching? Then they must accelerate at the same rate. I'm going to use the same trick I did with the ropes. I'm going to treat everything as one big mass. Let's label our forces, shall we? What are the forces acting on the 6 kilogram mass? Get the obvious one. I'll call that M1G. Normal force number 1. I have the applied force, which is 42.5 newtons. I just moved it. I don't like a force not coming or emanating from the middle of my mass. Is mass 1 pushing against mass 2? Yeah? Then there is a contact force. I'll call that FC, pushing in the opposite direction. What about that 6.75? That 6.75 is not acting on mass 1. I'm telling you that right now. What are the forces acting on mass 2? Let's zoom in because I can see some of you in the back row kind of squinting. That's about as big as I can make it. What are the forces acting on mass 2? I'll change colors. Get the obvious one. Boom, everything's better. Okay, bigger. I'll go in red for mass 2. What are the forces acting on mass 2? Get the obvious one. And by the way, the reason I say that, I'm trying to give you a nice systematic approach. Also, I've learned over the years, once you draw your first arrow, the rest of them seem to kind of come more naturally. It's when it's blank, kids always want to, well, I got to do the obscure nasty ones. Don't do the obscure nasty ones first. Relax. Take care of the obvious ones. So we got gravity, yes? Is it sinking into the ground like quicksand? No. Is it flying into the ocean? No. So I definitely agree that there is a normal force, and I'll call that normal force number 2. And if there was friction, I could use that later on in my calc. I would need to include that. But is there friction in this case, Elijah? How do you know? Mu is 0. No coefficient of friction. We're on ice. What other forces? Well, there is definitely an applied force of 6.75 newtons. I'll scribble it out here so I don't accidentally write it twice. What else? A contact force. And I'm going to argue, just like the tensions were the same, because it was the same piece of rope, I think the contact force is the same, but in opposite directions, because I don't think you can push against an object and have it push back on you with a different magnitude. Because forces come in Newton's third law. Is that okay? I got to go smaller now to actually write my equation. Who's winning? I'm going to guess the 42.5. That's a complete guess. Oh, if I'm wrong, I'll know because my acceleration will be negative, in which case I guessed wrong, quickly start over. Easy fix. but I think the 42.5. So I'm going to let to the right be positive, winner, to the left be negative, loser. Who's winning? Right is positive, yes. I'm just going to start, because this has got so many forces, I'll start right here, and I'm going to go totally along this line. So right is positive. I have a winner. And then I run into a loser. I run into a winner. I run into a loser. Did I get all of the horizontal forces? Did I look at more than one mass? Hey, what happens to the contact forces? Very similar to tension. They're going to cancel. I guess to find the contact force, which is the second thing it wants me to find, William, I'll have to go back and look at just one mass. Oh, just sounding kind of familiar. How would I get the A by itself? How would I get the A by itself? Oh, this is sounding really familiar. The acceleration is going to be negative 6.75 plus 42.5 divided by both masses, 6 plus 8.25. Okay. Negative 6.75 plus 42.5 divided by 6 plus 8.25. You get 2.5087, 2.51? Or am I wrong? Anybody else? Yeah. So we'll call this part A, find A. Manisha, what's the second thing they wanted me to find? Go look at one mass. Which one? Either one. I'm going to, let's see. Which one looks a little cleaner, a little easier? You know what? It looks like both of them have two horizontal forces. Oh, pick the one in which the contact force is winning. I think I'm going to look at mass 2, the one that I drew in red. Who's winning? Contact force, right? Because it's accelerating to the right. How do I know? Because I didn't get a negative answer when I assumed it was accelerating to the right. Who's losing? On the red force, on the red mass, only the 6.75, and that equals just mass 2 times A. Kelly, how would I get the contact force by itself? Cool. So it's going to be M2A plus 6.75, where M2 was 8.25. A was 2.51 plus 6.75. Those two blocks are pushing against each other with a force of 8.25 times that acceleration plus 6.2, was it 6.25? 6.75, Mr. Dueck. $27.4 newtons? And Hakeem, can you see, actually, this was almost identical to finding tension. The only difference was instead of a rope, we had a contact force. But the actual equations looked really similar. Yes, once again, contact force canceled. And then go look at an individual mass to find it. Next page. A curling rock, number 1, is traveling east across a sheet of frictionless ice, no friction. And we're looking down at it from the top. It bumps another rock and experiences a force that acts briefly to the north. What will be the path of rock number 1 after the bump? A, B, C, or I don't know if that line vanished. On mine it did, but there's supposed to be a line on D, an arrow pointing that way. Is yours there? Or is it just so connected? I think I've told you this was typed up in Word 95 for Mac, and we're in 2013. So slowly these diagrams, I'm going to have to retype them all. Yeah, I bought this off of a friend of mine, and he did a really good job. And it's on my list of things to get to, but that's lots of typing. So, curling rock, there's our top view. It's moving to the east. It briefly collides with a stationary rock, which applies a force. And we're asking, after the collision, what does the path look like? A, B, C, or D? Yeah, once again, we'll vote. Who says A? 1. Who says B? Who says C? Who says D? Convince him he's wrong. Why is it D? Yeah.
Because this to be A, you'd have to cancel out the force to the right.
Ah. I got to be careful. We'd have to cancel out its momentum to the right because there is actually no force. But I know what you mean. I don't see enough going on. I think he has a vector component traveling to the right. We apply a change in acceleration upwards. I think his new path is going to have a vector component to the right and a vector component upwards. So it's C or D. Why is C wrong?
You have to do an acceleration upwards.
We'd have to continue to be applying a force to do that one. Okay. Yeah? Sorry. So it says using principles of physics. Explain your answer. We just did. I want to get to example 6. It says this. A water bottle is drilled with many small holes so that it leaks when filled. If the bottle is filled and then dropped, what happens as it falls? A, the water stops leaking out. B, the water leaks out at the same rate. C, the water leaks out at a slower rate. Or D, water leaks out faster. I don't want you this time to raise your hand. We're actually going to do this experiment. But what I'd like you to do is right over here in this empty space, write down what you think the correct answer is. If you have a leaky water bottle and you drop it while it's in free fall, A, does the water stop leaking out? B, does the water leak out at the same rate? C, does the water leak out at a slower rate? D, does the water leak out faster? And then after you've made your guess, I want you to put a comma. Because here's the second situation. I didn't write this up. Second situation is, instead of dropping the water bottle, what if I start on the ground and I throw it up? On the way up, will A, the water stop leaking out, B, the water leak out at the same rate, C, the water leak out at a slower rate, or D, the water leak out faster? Okay? So the first situation is dropping it from a height, going down. Second situation is going to be throwing it straight up from the ground on the way up. Write down what you think for the first situation, comma. Write down what you think for the second situation, comma. Hakeem and Elijah, prepare to get wet. Why A? I picked on William a few times. He's showing off now, and we're good. Anyone besides my usual? Can you think of an approach that I might try and use to explain this? Free body diagram of the forces on the water. There's the water. Okay? And the bucket. Once I let it go, what are the forces acting on the water? Get the obvious one. And that's it in free fall. What are the forces acting on the bucket? Get the obvious one. In free fall. If those are the only forces, what can you tell me about the acceleration of the water compared to the acceleration of the bucket? Race. And did they both start out with an initial velocity of 0? And they're both undergoing the same acceleration? So can they possibly have different distances or displacements from each other? Which means the water's, in fact, I could do that if I was careful with a bucket, with literally a bucket full of water. I wouldn't trust the catchers at the bottom, but trust me, when I dropped it, the water would stay in the bucket the entire time. I'm trying to think of a way that I can do that in a way that isn't messy, disgusting, and dangerous. I've even thought about holding the bucket and just jumping off of a table, but it would slosh on the landing. But trust me, it would. They're both in free fall. What about on the way up? It's the same forces. Have I gone on a rant about how velocity and acceleration are independent of each other? Oh, we looked at a tennis ball a couple of days ago on the way up. That's the one that traps a lot of kids, because a lot of kids want to say, wouldn't the bucket be leaving the water behind? I'm telling you, they're both accelerating at the same rate, down at negative 9.8. Right? It says, using principles of physics, explain your answer. Explanation. Do I want to do example 7? I want to get to a cool video as well. So I'm going to skip. Maybe, can you remind me? I want to do this maybe next class. Maybe not, but I want to get to a couple of cool videos here. Homework. Oh, you know what? Number 1 we already did. The answer is A, right? Number 2, Mr. Dueck, the second diagram, they didn't give me masses. They said it was 3m and m. So make up a nice number for m. I would hesitate calling m 1 because then stuff might cancel, or I might think it cancels. Call m 2, which means it's 6 and 3. Sorry, 6 and 2. 6 and 3. 6 and 2. Call m 5. It's 15 kilograms and 5 kilograms. Whatever. You can handle it. Ooh. This is much nastier. Six, I think, is good. 8 is fairly nasty. I think we'll just give those for now, and I got a little video to show you here.